So Rust is kind of a big deal. In the past few years, it quietly went from a language praised by YouTubers and conference speakers to something much harder to ignore. What started as a side project at Mozilla back in 2006 is now the only other language besides C powering the Linux kernel. But, while Rust is still a niche language compared to some of the giants, its influence is wildly disproportionate to its market share. A few days ago, for instance, the Ladybird browser announced something that would have sounded almost radical 5 years ago. They're rewriting parts of the browser in Rust. In their announcement, they mentioned that they'd been looking for a memory-safe replacement for C++ for a while. Swift was evaluated, but the interrupt story never fully landed, and once you step outside Apple's ecosystem, the ground gets shaky. Rust, on the other hand, comes with a mature systems ecosystem and a contributor base that already speaks the language fluently. What's interesting is that this wasn't their first look at Rust. Back in 2024, they rejected it because the web platform object model is soaked in 1990s-style object-oriented design. When building a browser, you'll run into deep inheritance hierarchies, garbage collection assumptions, and a very C++-shaped worldview. Rust's ownership and borrowing model doesn't naturally map onto that architecture. But both Firefox and Chromium have already been introducing Rust into critical components, so Ladybird concluded that pragmatism eventually beats aesthetics. And the port itself is where this story becomes very 2026, because, you've guessed it, the translation was done using Claude Code and Codex. But please don't rage close the video yet, because they actually did it in a reasonable manner, showcasing that LLM code generation can be useful when done correctly. The constraint from day one was to aim for byte-for-byte identical output. The entire process was directed by humans with hundreds of tightly scoped prompts based on very detailed planning. After the initial pass, multiple adversarial reviews were run using different models to hunt for subtle mistakes and non-idiomatic patterns. The result was roughly 25,000 lines of Rust written in about 2 weeks. What's impressive is that every AST produced by the Rust parser matches the C++ version exactly, and every bytecode sequence is identical. There are 0 regressions across more than 60,000 tests. Beyond test suites, the Ladybird team ran lockstep browsing sessions where both the C++ and Rust pipelines executed simultaneously, verifying identical behavior for every JavaScript fragment encountered in the wild. But if you inspect the code, you'll be surprised to find out that it doesn't look like textbook Rust, but like C++ wearing a Rust costume. That was intentional because their goal was compatibility. Even C++-style register allocation patterns were mirrored to ensure identical bytecode output. Idiomatic cleanup will come later, after the C++ pipeline can safely be retired. The Ladybird experiment proved that AI can handle the transcription of logic, but it also highlighted a big risk. AI is great at translating C++ into C++-flavored Rust, but it doesn't yet have the capability to refactor a codebase into something truly idiomatic. Ladybird gained safety, but they also inherited the architectural technical debt of the 90s in a different syntax. The main takeaway of this story is that thanks to well-managed code generation, we can expect more situations when Rust will replace the established C and C++ codebases. And this leads us to another interesting Rust success story inside one of the largest communication platforms on the planet. WhatsApp is used by over 3 billion people every day. If Rust helped Ladybird modernize a browser pipeline, the WhatsApp story is about performance and massive scale. To understand why Rust ended up there, you have to rewind to 2015 and the infamous stage fright vulnerability. The vulnerability was in the way the operating system's media processing libraries handled certain files, meaning WhatsApp and other apps had no ability to fix the issue themselves. So WhatsApp took an internal C++ media library originally built to normalize MP4 files and extended it to validate media structure aggressively. The idea was to detect malformed files before they ever touched the vulnerable OS code. It worked, but it introduced a new problem because that validation layer itself processed untrusted input written in C++, which means the thing designed to prevent memory corruption bugs could itself contain memory corruption bugs. And here is your awesome trivia for the day. In 2006, Graydon Hoare, a 29-year-old computer programmer at Mozilla, came home to his apartment in Vancouver to find the elevator out of order. This was a common situation in his building, with the elevator often incapacitated because of a software crash. Hoare lived on the 21st floor and, as he climbed the stairs, he got really angry. He knew that elevator software is almost always written in C or C++, which are languages that are prone to memory errors that lead to crashes. He realized that a simple null pointer, or use after free error, was the reason he was currently sweating through his shirt on a stairwell. That night, he started designing a new language in his living room, planning to make it impossible to write those kinds of memory-related bugs. So, in a way, we got Rust because C++ couldn't keep an elevator running. Back to the video, the team decided to look at Rust, but instead of cautiously introducing Rust into isolated corners of the existing codebase, they rebuilt the entire media consistency library in parallel. Both implementations ran side by side, subjected to differential fuzzing, extensive integration coverage, and a large suite of unit tests designed to guarantee behavioral equivalence. And the scale of the rewrite is substantial. Around 160,000 lines of C++ were replaced with approximately 90,000 lines of Rust, including tests. The resulting implementation turned out to be leaner, with measurable gains in performance and runtime memory usage. But the real significance lies beyond code metrics. What makes this effort remarkable is where it runs. The Rust library is distributed to billions of devices across Android, iOS, macOS, web clients, and wearables. It operates not only within WhatsApp, but across the broader Meta ecosystem, including Messenger and Instagram. Deploying client-side Rust at that scale effectively stress-tests the language under some of the most demanding real-world conditions imaginable. If there were fundamental production weaknesses, this environment would have exposed them quickly. Instead, the rollout became what the team believes to be the largest client-side Rust deployment to date. So we can now see a broader industry transition. For decades, C and C++ defined systems programming by default, but at a lot of companies, that default is shifting. Rust is unlikely to displace legacy systems overnight, but it is increasingly positioned as the containment layer for high-risk boundaries. Browsers are adopting it for security-critical components, messaging platforms are distributing it to billions of users, the Linux kernel now accepts it alongside C. But despite all of the success, a very important thing to remember is that Rust is not a one-size-fits-all solution. A few days ago, a blog post titled "Farewell Rust" got quite a bit of traction on social platforms. What makes that post interesting is not the usual "Rust is too hard" complaint, because it is written by someone who genuinely understands low-level programming, who loved C, who embraced Rust for the right reasons, shipped a real product in it, made money with it, and still walked away. And that's because, despite its growing popularity, Rust isn't a good solution when building for the web. The web is not primarily a systems programming problem. Templating is a good example. In the TypeScript world, your UI components are type-checked by default. If you rename a prop and the compiler screams, autocomplete works, and refactors are mostly mechanical. In Rust, if you use string-based template engines, your views and your data drift apart unless you're extremely disciplined. If you use macro-based DSLs for type-safe templates, you regain safety, but you pay in compile times and macro complexity. So every small visual change goes through the compiler pipeline. This quickly becomes a problem because web development is visual and iterative. You tweak labels, adjust layouts, and rename fields constantly. The feedback loop matters more than raw execution speed. SQL is another pressure point. Rust's SQLX is impressive with compile-time query checking. But the moment your queries become dynamic, because real applications have filters, optional clauses, search parameters, you either lose the compile time guarantees or fight the abstraction. Meanwhile, JavaScript query builders give you practical type inference without needing to spin up a database at compile time. Of course, none of these issues are catastrophic, but it is cumulative friction. So while it is extremely successful when paired with the right problem, Rust is still far from being a universal tool for the average developer. If you like this video, you should consider joining our community where I'm posting more dedicated weekly content. Please don't forget to smash all the buttons, and until next time, thank you for watching.